Okay, on today's lesson, we want to go back to ag construction with electrical wiring and show what we call the power equation, or the power square, which is demonstrating the mathematical relationship between power, measured in watts, voltage, and amperage that's happening in an electrical circuit. Previously, with Ohm's law, we had brought in voltage, amperage, and resistance, the electrical friction, and showed its relationship, what's happening in the wire. Then we're going to add one more factor here, which is power rating, the power of your device, whatever appliance you're running, whatever tool you're running, audio devices, stuff like that. It's always measured in a power output or wattage, and how we get that power output or wattage that's available for the device to use. So in this particular one, we're representing the letter P for power. Is going to represent electrical power, which is in watt units. We're using that instead of W. We're using E for electrical pressure for voltage. So I want to show volts will be our units. Can I put that by itself? And then current for amperage, once again, would be measured in amps, or the flow of electrons. So the first part of the formula here is how do we determine power? Power, watts equals amps times volts. We're going to multiply amps and volts together and come up with the number of watts of power that's available here, power output. So if we have 20 amps flowing through a wire with 120 volts pushing it, for the most part, 120 times 20 is going to give us down here 2,400 watts, which would be 2.4 kilowatts, because the power company is going to measure it in kilowatts, but we're just going to stay with watts right now. So 2,400 watts equals 28 amps times 120 volts. That's what would be available. And then we can also take it in algebra. We can take this formula, we can flip it around, we can solve for amperage, we can solve for voltage. And when we do that, then let's say we take amperage first. And on the diagram, we can set it up so you can see. People like to see the diagram, but on this demonstration, we'll just show the formulas. All right, so if I'm going to solve for amperage, I'm going to have to take basically power divided by voltage. So we flip it around and say, okay, well, how many amps are flowing through a wire? Well, we've determined, let's put that down here so our visual people can see. I is amps, and then watts divided by volts. All right, so we're going to solve for amps, and we determined that we happen to have 2,400 watts on a 120 volt circuit. Then we divide that, then I would say, okay, at that given point, we have 20 amps flowing through the wire. If all the devices in the circuit that are on, and it uses 2,400 volts, that means there's 20 amps flowing through the wire at that point. So we have to make sure that our electrical wire is big enough to handle 20 amps, and we have a 20 amp breaker. If we exceed 20, the breaker trips before the wire melts and causes major problems. So that's our mathematical relationship here. Not complicated, but the electrician's part of the planning process for wiring the house is to find out what the customer wants on these circuits, what's going to be on these circuits, and if we exceed that, then that's what we have the overcurrent protection for. Then algebraically, if we want to solve for, let's say, voltage, we're going to figure out how much voltage is in the wire, given amperage and power that's happening at that time, we can solve for voltage. So mathematically, we can take voltage, and we can take power in watts divided by amps. So once again, we can put that volts equals watts divided by amps. So in the circuit, we're not sure about the voltage rating. We could do that mathematically. We say, okay, I happen to have 2,400 watts on the circuit, and the ammeter said there's 20 amps flowing through the wire, then at that given point there should be 120 volts. So the biggest thing is, here's what's on the circuit. Usually you could plan ahead and say, if you got a 20 amp breaker and the wire can handle 20 amps, then your devices plugged in cannot exceed 2,400 watts on that particular circuit. And that will go back to your service entrance panel where it happens to be located. And you got a breaker that's got 20 amps on that and says, okay, now that's what you get. If you exceed that, that's where we're going to have things. In some of the older houses, older wiring, circuits haven't been updated. There may be an incident where the microwave, the toaster, the coffee pot, on the same circuit, they happen beyond that time, and the breaker trips. Breaker doesn't trip any other time, but it trips because those three things happen to be exceeding that load. So that is possible. So the biggest advantage here is to make sure your wires and your breakers are the right size for what's going to be on the circuit. And each circuit can be taken care of like that. So that's the mathematical relationship for power square and determining power, basically the load here, or the watts, the voltage and amperage for a particular circuit. We're going to try some practice problems and make sure you get the hang of it.